Hello everyone. In this video, we are going to discuss about line spectrum of hydrogen from the chapter 2 Structure of Atom, class 11 Chemistry. You see, when an electric discharge is passed through gaseous hydrogen, the hydrogen molecules dissociate and becomes hydrogen atoms. And these hydrogen atoms will be in the excited state. And these energetically excited hydrogen atoms produced in this case can emit electromagnetic radiations such as infrared radiations, ultraviolet radiations, visible light, etc. And the excited hydrogen atoms can emit electromagnetic radiations of that is, when electric discharge is passed through the gaseous hydrogen, it dissociates into hydrogen atoms, and these excited hydrogen atoms can emit electromagnetic radiations of discrete or different frequencies. When this emitted radiation is passed through a prism, it produces a spectrum in the photographic plate. And that spectrum contains different or discrete set of lines called the line spectrum of hydrogen, which is actually an emission spectrum. Line spectrum of hydrogen, that is also called as emission spectrum, which is also called as atomic spectrum of hydrogen. You see, the hydrogen spectrum, it is known as a line spectrum because the light or the radiations emitted by the hydrogen gas consists of a series of sharp lines. See, the lines are caused by the absorption and emission of energy of electrons in the hydrogen atom. When electrons absorb energy, they jump to higher energy levels, and when they emit energy, they come back to or descend to lower levels. That is, suppose an electron is initially here. When it absorbs energy, it gets more energy and it jumps to higher energy levels. Okay, and when they emit energy, they come back to their lower levels. When they come back to their lower energy levels, the different electrons take different paths for their return. Different paths are actually associated with different energies, which results in different spectral lines. The hydrogen spectrum consists of several series of lines named after their discoverers. The series of lines are Lyman series, Balmer series, Paschen series, bracket series, Fund series. So Lyman series, Balmer series, Paschen series, bracket series, Fund series. So L, BP, BP. See, the Swedish spectroscopist Johannes Rydberg noted that all series of lines in the hydrogen spectrum could be described by the following expression. That is, nu bar equals 1 by lambda, which is equal to 1,09,677 into 1 by n1 square minus 1 by n2 square centimeter raised to minus 1. See, in this expression, this nu bar or 1 by lambda, that is actually called as wave number. And n1 can have values 1, 2, 3, 4, 5, etc. n2 can have values n1 plus 1, n1 plus 2, n1 plus 3, etc. That is, when n1 is equal to 1, n2 will be equal to n1 plus 1, that is 1 plus 1, 2, n1 plus 2, that is 1 plus 2, 3, n1 plus 3, that is 1 plus 3, 4, 5, etc. Okay, similarly, when n1 is equal to 2, n2 can have values 3, 4, 5, 6, etc. And you see, this value 109677, you know this value 109677 677 centimeter raised to minus 1, which can be approximated to 1.097 into 10 raised to 7 meter raised to minus 1. This value is called as Rydberg constant for hydrogen. Okay, so you see the Swedish spectroscopist Johannes Rydberg noted that all the series of lines in the hydrogen spectrum could be described by this expression, that is nu bar equals 1 by lambda into Rydberg constant into 1 by n1 square minus 1 by n2 square. Okay, this value which can be approximated to this 1.097 into 10 raised to 7 meter raised to minus 1, this is actually known as Rydberg constant for hydrogen. Now you see the series of lines correspond to n1 equals 1 is actually Lyman series. The series of lines correspond to n1 equals 2, that is Balmer series. Corresponding to n1 equals 3, we have Paschen series. Corresponding to n1 equals 4, we have bracket series. Corresponding to n1 equals 5, we have Fun series. That is, you see in this formula, when n1 is equal to 1, we will be considering Lyman series. When n1 is equal to 2, we will be considering Balmer series. When n1 is equal to 3, we will be considering Paschen series. When n1 is equal to 4, bracket series. n1 equals 5, Fun series. And what about n2 values? You see n2 will be greater than n1. That is, n2 can be n1 plus 1, n1 plus 2, n1 plus 3, etc. That is for Lyman series n1 equals 1. So this n2 can have values 2, 3, 4, 5, etc. up to infinity. Similarly, if you consider n1 as 5, then n2 will be 6, 7, 8, 9, 10, etc. up to infinity. That is, you see, for the Lyman series, n1 equals 1, n2 can have values 2, 3, 4, 5, etc. And corresponding to, we will be getting a series of lines. We will be getting some electromagnetic radiations which lies in the spectral region. That is its spectral region is actually UV radiations, ultraviolet radiations. That is, during Lyman series, in the Lyman series, we will be getting ultraviolet radiations. And for Balmer series, n1 will be 2, n2 can have values 3, 4, 5, etc. And its spectral region actually lies in the visible region. Okay, that is, visible region means our visible light. Violet, indigo, blue, green, yellow, orange and red colors, no, they are actually called as visible light. Now, for Paschen series, n1 equals 3, n2 can have values 4, 5, 6, etc. And its spectral region is actually infrared region. That is, during Paschen, that is when we consider this Paschen series of lines, we will be having some infrared radiations in that spectral region. Similarly, for bracket series, we have n1 equals 4, n2 can have values 5, 6, 7, etc. And its spectral region is actually infrared region. Similarly, for Fun series, n1 is equal to 5, n2 can have values 6, 7, 8, 9, etc. And its spectral region is actually infrared region. That is, we will be having infrared radiations in that spectrum when we consider Fun series. Okay. Now, let us see the transitions of the electron in the hydrogen atom. This diagram actually shows the Lyman series, Balmer series and the Paschen series of transition. Similarly, we can have bracket series of transitions, Fun series of transitions, etc. So here you see, when we consider Lyman series, you see this is actually the energy level corresponding to n equal to 1. This is actually the energy level corresponding to n equal to 2, n equal to 3, n equal to 4, 5, 6, etc. up to infinity we can have. And you see here, this is actually in the order of increasing energy. That is, for n equal to 1, that is the lowest energy level, it will be having less energy. But when we consider n equal to 2, 3, 4, 5, etc., when we go from here to here, its energy actually increases. Energy of each level actually increases. Okay, as the n value increases. So here you see, we know that in the Lyman series, n1 can have values 1, n2 can have values 2, 3, 4, 5, etc. So here n1 equal to 1, that is the lowest level. Now, if an electron is getting, if the transition of electron is from n equal to 2 to n equal to 1, we will get Lyman series. Similarly, n equal to 3 to n equal to 1, n equal to 4 to n equal to 1, n equal to 5 to n equal to 1, etc. we will have Lyman series. Okay, and in the Lyman series, the spectral region is actually the ultraviolet radiations. Spectral region consists of UV radiations. Similarly, when we consider the Balmer series, which actually gives the visible radiations. Okay, for Balmer series, we know that N1 that is equal to 2. That is, transitions will be taking place to what? N equal to 2 value from 3, 4, 5, etc. Okay, that is, while we are considering Balmer series, N1 will be equal to 2. N2 can have values 3, 4, 5, etc. So we have to consider the transitions from N equal to 3 to N equal to 2, N equal to 4 to N equal to 2, N equal to 5 to N equal to 2, N equals 6 to N equals to, etc. Okay, and you see, if you consider Passion series, it actually gives us a spectral region, which is the infrared region. Okay, we will be getting infrared radiations during this transition. So in this case, for Passion series, we know that N1 can have values 3, N2 can have values 4, 5, 6, etc. Okay, so transitions of the electrons that will be taking place to N equal to 3 level from 4, 5, 6, etc. Okay, so N equals 4 to N equals 3, N equals 5 to N equals 3, and an electron is getting transited from, it is coming from N equals 6 to N equals 3 level. Okay, all these transitions of the electron will give us the infrared radiations, and this is actually corresponding to the Passion series of transitions. Okay. Similarly, we can have bracket series of transitions, fun series of transitions, etc. Here I have just shown Lyman, Balmer and Passion series. Okay, now you see, of all the elements, hydrogen has the simplest line spectrum. If you consider heavier atoms, line spectrum becomes more complex. So you see, line spectrum, it is actually the line spectrum of element, it is actually unique. Okay, that is, hydrogen will have a unique line spectrum which other elements cannot have. Okay, that is, if you consider the line spectrum of other atoms or other elements, you will get a different one. Now, there is a regularity in the line spectrum of each element. Okay, so line spectrum of element that is unique, for each element is unique, and there is a regularity in the line spectrum of each element. So, in this video, we have discussed about the line spectrum of hydrogen. I hope it is clear to you. Thank you.